So, I'm now going to change gears. This lecture is about section 6.5, which talks about two things. One is what's called a principal value integral, which is different in a certain sense from improper integrals that you studied in first year. And we're going to talk about indented contours. And we're going to have an indentation near the singularities. We'll see how that happens. But before I talk about indented contours, I'm going to talk about real principal value integrals. So the PV stands for principal value. And the principal value of an integral, a definite integral of a real variable from x equals a to b, where f is singular at some point in between a and b, is singular at the point c. The principal value of this is the integral from a to just short of the singularity, plus the integral from just past the singularity up to b. And we take the limit as the distance that we stop short and that we've gone past the singularity goes to 0. And the important thing is that we stop short at a distance r and we continue on at a distance r from the singularity in the middle. So we have to be symmetric. That r has to be the same as that r. And that's what the principal value is going to be, because the symmetry about the singularity allows the infinities to cancel. And it turns out that that's actually what's wanted in some applications. So as an example of a principal value integral that you might have seen in first year, if you look at the principal value of the integral of just dx over x from -2 to 2, it turns out that the value is 0. And somehow that is sensible, because sure, the areas are infinite, but they're symmetric. And so you expect the area, this positive infinity area, to cancel that negative infinity area. And it does that if you do it symmetrically. So if we look at just the integral from -2 up to just short of 0, so integral from -2 to minus epsilon of dx over x, we get the antiderivative of dx over x is log x, of course. So we get log of minus epsilon minus log of -2. And we're happy with logarithms of negative numbers in this complex variables course. That's log of epsilon plus I pi minus log of 2 plus I pi. And the I pi's go away, so we wind up with a real answer, which is really nice. That's what we want. And the real answer is log of epsilon minus log of 2 for this integral. And then if we do the other half of the integral from past the singularity up to 2, so integrate from epsilon to 2 of dx over x, well, you just get log 2 minus log epsilon. And when we add these two together, right, you're adding these two integrals together, the logs will cancel and the log of epsilons will cancel. And they add to 0, and the singularities cancel because the strength of this one is exactly the same as the strength of that one. But in fact, you were taught in first year that that integral diverges. The integral from epsilon to 2 of that diverges. And certainly if you let epsilon go to 0, this becomes minus infinity. And this one becomes positive infinity. If we don't do the integral on the other side symmetrically, so we integrate to some other small number, minus s, then the singularities aren't going to cancel. And you're going to be left with either plus infinity or minus infinity or anything in between, depending on exactly how you choose to do the asymmetry. And sometimes that's the right answer. The question of when you're supposed to use the principal value and when you're supposed to look after the infinities is a question that really depends on the context of your problem. And we're not going to cover that much, but I do want to assure you that present value integrals are useful, but they're not what we always want.